So this is our final sheet in this semester, 11.1. It's all about ordinary differential equations, short ODE. This is the usual abbreviation. I'm talking about ordinary differential equations, which means that we have just a single independent variable x as usual, and we are looking for an unknown function. And as you see in the first example right here, we have meanwhile introduced a very short kind of notation. So that's what we usually do. So from now on, we do not use the notation like y equals f of x equals whatever. We just abbreviate this with y. And also, it's quite important now to make yourselves a little bit more independent from these notations, because it's a good idea to use the symbol y for what it is, because what is it? It is a variable, and that's most important. It's clear we're looking for y as a function of x, but this is just, you could say, a sort of the way we look at it. It's not always so easy to say that y is dependent on x. It might be that x is dependent on y also, whatever. There's a certain relation between the two, and we should allow the variable y to live its own life, you could say. Okay, so it's like sort of x and y are coupled to each other, and we're looking for the exact let's say relation between x and y. And in doing so, there's a very important first method, which is called separation of variables, which we use now. And this is especially useful for these so-called first order ODEs. First order, well, here the definitions are relatively clear. We're talking of first order differential equations if the highest order derivative that's inside this equation is the first derivative. And this is the case, as you see everywhere in this first exercise. Now, for the first example, this is relatively general. It tells us that y prime should be equal to some constant a times y itself. So this is relatively familiar to us. We could even guess the solution, because this must be a function which is proportional to its own derivative. And as we know, this is the case for exponential functions. So it's easy to guess, but at the same time, we want to get familiar with this standard technique of separating variables. So let's do so. And right for the first one, this is the usual way also of writing it down. First of all, we remember that y prime is just a short notation for taking a differential or building or constructing a differential quotient, like dy over dx, right? So this is the classical way of writing down what we're doing. We are calculating the rate of change of y related to an according increase of x. And so that's what we do. We use this differential quotient or fraction notation, and then we set it equal to what it is, a times y. And now comes the separation process, which is to be performed as follows. We must take care that everything containing y is put on one side of the equation, while all the x terms on the other side, are placed on the other side. So it's important that you have one side of the equation just described using y, and the other one exclusively described using x. And the final step will be then, after we achieve this, we make ourselves familiar with the fact that if even a differential equation is given, which holds for any value of x and corresponding values of y, it means that it must be allowed to take an integral. The best thing would be to take an indefinite integral on both sides. So in the end, the integrated version of the equation will still be true, because what we're doing is just summing up, and we're summing up according to what the coupling is between x and y. The only perhaps a little difficulty is after we solve the last integral, we have to put an integration constant on one side of the equation, not on both sides, because both sides would be, you could say it's just too much, right? Because otherwise we could put these two constants together and then in the end it's only one. But it's important that a first order differential equation must contain in the end, in its solution, it must contain one so-called free parameter, which we call it a solution parameter. It can be chosen freely, and it turns out that very often this original integration constant I'm talking about gets, you could say, transformed to be a constant factor of the term that we find as a solution. This is quite a characteristic effect. We will observe it soon. Now, look, here I have my dy over dx, and it equals a times y. So in this special case, there's no x at all, aside from the differential. So what we do is we take the differential x to the right side, to the right-hand side, and then we divide by y, which is a little bit dangerous because we must demand that y is not equal to 0 in order to be allowed, you know, because we can't perform a division by 0. So that's nothing special, you know it. We've had this all the time, but this time, this is, you could say, a preliminary restriction. The reason why it's preliminary is it will turn out, in most cases, in the end, that y equals 0 is not a problem at all. It's not even a problem if y equals a strong 0. As you remember, I've been saying, a strong 0 like the 0 function. Even this is usually an allowed special solution. So in other words, it's sometimes hard to explain. We do divide by y. We must exclude y equals 0 preliminarily, but this restriction may be taken away afterwards. Okay, so you should remember it and check it afterwards. So now, dividing by y, we get dy over y. And this is very familiar to us. We remember that this is a case where the integrated version will be something logarithmic. That's typical for this kind of equations, right? And on the right-hand side, it's quite simple. If we take an integral on both sides, here we must integrate over y, of course, here over x. Accordingly, it means that here we have integral dy over y, which is well known to be ln, natural logarithm of the absolute value of y. Don't forget the vertical bars, because they're important. You see it here. It would be, leaving them away would mean suddenly that y lower than 0 would not be allowed, because the logarithm isn't well defined for negative arguments. But there is no reason to exclude negative values of y. So that's another time where we encounter this situation in which it is important to use the vertical bars for the negative values of y to be allowed. But as you see, even here, y equals 0 is not allowed, and that's what we excluded from the start. So that's quite a well, reasonable thing to do, to exclude it, but we may check afterwards. Now, right-hand side, easy. This is a constant. The primitive will be a linear term, a times x, whatever a is. We say a element r, so it might even be 0, but that's just an uninteresting special case. And now it happens that we have to add a freely chosen integration constant, which I called C1 because this is preliminary. It will be renamed several times until we find the final form of the result. Now, what do we have to do? We have to isolate y. And to do so, we just take the exponential on both sides just to cancel this logarithm, as you know. So e to the power of ln of something cancels out, and the argument stays there. It's still absolute value of y. On the right-hand side, now this is an important effect that occurs very, very often what we get is exponential, so e to the power of the whole thing, which is a times x plus c1. And now, since we have a sum in the exponent, we may easily put this in a product form, as you know, by the well-known rules of potency, right? Power rules. So what we have is e power a times x times e power c1. And now it's interesting. While this constant c1 is element r, suddenly you could say it transformed to a certain factor, e power c1, but this factor isn't element r anymore, it is definitely positive. Why is it? Well, because exponential terms of this kind are always greater than 0. So that's an important effect. Now, in the next step, taking away the vertical bars to isolate y, we find that inside here, y could also be negative or positive, whatever, but not 0. So by taking away the absolute value signs, we are forced and allowed at the same time to make a case distinction here and say plus or minus C2. This was a renaming, right? This C2 is positive. So C2 times E power A times X. Now, in the end, I can say this is a positive constant with an additional plus or minus sign. So altogether, this is non-zero. It may be negative again. I rename it another time. I rename this to be just C. And now this is a factor element R to be, well, exactly speaking, it's a factor element R without 0. But now we go back to our preliminary restriction where we said y must not be 0. But if this constant would be 0 anyway, if we just allow it, so then we get y equals 0 even strongly, which means y is the 0 function. So y equals 0 for all values of x. And now the question is this a valid solution of the differential equation or is it not? And if you go back here to see, inserting y equals 0 as the 0 function here, we get an a times 0, which is still 0 for any value of x. And the rate of change of the 0 function equals 0 for all values of x. So this equation is fulfilled. And so you could say this is the final test, which allows us afterwards to say it's no problem if y equals 0. It's not a problem either to choose this constant to be 0. And this is an important step, which I put down here as a side note. Please remember for the future, most, you could even almost say all, for practical purposes, all linear homogeneous systems. I say system because this is also part of system theory. We're describing technical systems in a sense. All these systems are stable. And this means mathematically they can be, or technically speaking, they can be in an idle state, sort of doing nothing, right? And it means in mathematical form, it means that the null function y equals 0 strongly for any value of of x, that this is a valid solution of such a kind of equation.